Hi, we've got a worked example to go with mini lecture 2. This is problem 2.1 from the question sheet. And the problem is that we have a filling line, which is filling bottles in an automatic process. We want to know something about the variation and the average of the fill of each bottle. So we've got 7 measurements. 7 measurements isn't very many, but the methods we use here obviously could be scaled up for a larger number of measurements. The question wants us to create a histogram of the relative frequency density, find the mean, find the median, compare these two, find the unbiased standard deviation and find the interquartile range, and again compare with the standard deviation. First of all, let's create a histogram. We've only got 7 data points, it's not very many, so we need to select a number of intervals. So we don't have a lot of choice. I'd say that you couldn't go more than 3, and even 3 we obviously don't have many data points in each one. And so what I've done is I've made them a variable width, and that at least will help to even out the number of data points that sit within each interval. It's perfectly fine to have varying width of each interval, because when we find the frequency density we're dividing by the width, so that takes account of the fact that they are different widths. So then we count the number of data within each interval, 3, 3 and 1. When n equals 7, that's the total number of data points. We want to find the relative frequency density, so we take the frequency 3 and we divide by 3, that's the width, that's what turns it into a density. Dividing by the width turns it into the density, and then we divide by 7, that's the total number of data points, and that makes it into a relative frequency density, 0.143, and we do likewise for the other 2 intervals. Now we can sketch this. Here's me doing it. Again, I'm doing it with pencil, pen and ruler and paper. This is actually faster than doing it on Excel. You pick some scales which are convenient to read off. So we've got 1 centimetre is 0.1 reciprocal gram on the y-axis, and 1 centimetre is 1 gram on the x-axis, and that makes it simple enough then to scale what you're trying to plot using your ruler. And there we go, that's our histogram. Now there's not a lot of data, so it's only very basic, but you can see we have turned 7 data points into the beginnings of a distribution. Find the mean, you know how to do that. You add them up and divide by the total number of points, 400.4 grams. Find the median, compare to the mean. Okay, so we put the points in order. We've got 7 points, and so there's 1 in the middle. It's an odd number of points. There's 1 in the middle on its own, and that's what we identify as the median, 401 grams. 401 grams is very similar to 400.4 grams. Would you expect it to be the same? Well, sometimes you do, sometimes you don't. When the data is very skewed, if it's got, for example, a single very large number, or perhaps a single very small number, that will skew the mean. The mean has a contribution from each data point, so if there's just one data point that's really, really big, that will have an impact on this and affect what the mean is. The median isn't affected by that. You could have a very large number here or a very small number here, and it wouldn't affect the median. So they measure slightly different things. If the data is symmetrical, then the mean and the median will come out as being pretty similar. But if it's skewed, if it's got some points at the one end or at the other end, then you'd expect to see a difference in those 2 measures of where the middle is. The unbiased standard deviation, we saw how to do that in the mini lecture. It's the difference between the mean and each data point squared and then summed. And for the unbiased case, we divide by n-1. And remember, we use the unbiased standard deviation to estimate what the standard deviation of the original population was, rather than the standard deviation of the data set that we've measured. And what we're really interested in is what's happening on the production line. Of all the different bottles that get produced every day, we want to know what the distribution is of those bottles that's more important than what the particular sample that we have is. So using the unbiased standard deviation will give a better estimate of that. It comes out at 1.62 grams. The interquartile range, well, to do that we were using the method of dividing the data into two. In this case it's an odd number, so we leave the one in the middle out. We have 1/2 of the data there and 1/2 of the data here, and then we find the median of each of those, and with the 3 data points we just take the middle one, 399 and 401. So the interquartile range is equal to 2 grams. Okay, how do we compare them? Would we expect them to be like that relatively or not? Well, let's have a think about what our assumptions are in some of this analysis. So we found our median value, and let's consider the normal distribution that we've assumed when we're calculating a mean and a standard deviation. So that's a normal distribution, and we can identify the interquartile range on this. It's the middle region which contains 50% of the data. So that's the middle region which contains 50% of the data, 50% there, and you can work out the number of standard deviations to the right and to the left which amount to that much. It's about 0.67 standard deviations. Either side of the median will give 50% of the data. Whereas within 1 standard deviation of the mean, you'd expect to get about 68% of the data. So how does that compare with what we've got here? The interquartile range is 2 grams. So if that was on here, it would be 1 gram either side of the mean value there, 1 gram either side. Whereas the standard deviation is 1.62 grams. So that would be 1.62 grams there, 1.62 grams there. Okay, so that's making sense. The standard deviation is more than 1/2 of the IQR. That's half of the IQR, and that's 1 standard deviation. So that would be 1 gram in our case, and that would be 1.6 grams. So that looks about right. So what this means is that the assumption of a normal distribution is looking reasonable in this case. And that doesn't always need to be true. If your data is completely flat, if it's evenly distributed, then your IQR and your standard deviation would look very different. Would look very different when you plot them like this. When your data is normally distributed, you will find that they are proportionately matching each other. And in this case, they match each other pretty well.